Let's try to solve this question here. The diameter of a hole in a steel plate is 1.35 cm at 25 degrees Celsius, and they tell the coefficient of linear thermal expansion of steel is 1.2 times 10 to the power negative 5 per Kelvin. Okay, so let's try to sketch out a situation. So we probably have plate, and this plate here has a circular hole inside because they give you the diameter. Okay, so let's assume this is the square plate. What shape I don't think is very important. But let's say your steel plate here is a square, then inside this plate there's a hole. Then they let you know that the diameter of this hole is currently 1.35 cm. Okay, 1.35 cm converted to meter is 0.0135 meter. Okay, and this is the situation when the temperature is 25 degrees Celsius. Okay, the coefficient of linear thermal expansion of steel is 1.2 times 10 to the power negative 5 per Kelvin. So linear thermal expansion means by this is alpha, not beta, not gamma, because it's linear. So linear thermal expansion for steel is 1.2 times 10 to the power negative 5 per Kelvin. Okay. Then they ask you, calculate the cross-sectional area of the hole when the temperature of the plate is increased to 175 degrees Celsius. So what happened is you are going to heat up this plate here until you reach a new temperature of 175 degrees Celsius. And I believe you are aware that the whole plate here will experience expansion. The whole plate here will become bigger. So what should happen to the hole? Does the hole get bigger or the hole get smaller? Okay, if you think about it, it should be logical that the hole should be larger right now. Okay, why can you think so? You can think of hole, right, made of, okay, let me sketch it here. Hole are made of atoms at the boundary. Okay, so if you have atoms surrounding the border and the inside of the border there's nothing, then that's the hole, right? Okay, inside if there's nothing, then that's the hole. Then if you heat it up, what happens is the particles will vibrate more vigorously, then they push all the particles apart. So the distance between the particles will get further away, because they are vibrating vigorously, then they push each other apart. So the distance between one particle and another particle become more distance. Okay, so I believe you can see that if the particles become more distant, what should happen is the size of the hole should be increasing as well. Okay, so the area of the hole can also be calculated using area expansion as well. Okay, so this is the original area of the hole. This is a new area of the hole. You can see that the area of the hole should get larger because the particles vibrate more vigorously and push each other apart. Okay, so that's the idea. So we know that we are talking about the area of the hole being expanded. So this is actually area expansion. So area expansion, we know that the new area, okay, the new area, cross-sectional area of the hole when the temperature is increased to 175 degrees Celsius. So it's a new area of the hole is equals to the old area of the hole, then 1 plus beta delta T. Okay, this is what we know from earlier. Then beta is not given over here. Beta is a coefficient of area expansion. But we know that the coefficient of area expansion is just twice the coefficient of linear expansion. So you can further modify the equation to be 1 plus, we can transform the beta to be 2 times of alpha and change of temperature. Now we have all the values that we need. We are just left with substitution. So the new area, which is what we want to find, is the old area. Old area can be determined using pi r squared because it's a circular area. But because they give you diameter, not radius, you have to take the diameter value, divide by 2 to obtain the radius, then only you square it. Okay, then you have 1 plus, you have 2 alpha delta T. Okay, now it's really substitution time. So pi, the diameter is 0.0135 divided by 2. You get your radius, then you square it. and you have 1 plus 2 alpha. Alpha is 1.2 times 10 to the power negative 5, and the change of temperature is from final, it's the final, which is 175, minus the initial, which is 25. Okay, then from here, if you perform a calculation, I believe you get your area to be equals to 1.44 times 10 to the power of negative 4 meters square. Okay, so this is the new area of the hole right now after the temperature has increased from 25 to 175 degrees Celsius. Something that I think you all might be wondering is, why is alpha, when it's given in the unit of Kelvin, can be substituted inside even when the temperature is in degrees Celsius? Okay, the temperature, the change in temperature is measured in degrees Celsius, but you are going to multiply it with alpha, which is measured in per Kelvin. Is it okay to do so, mixing up the temperature unit? Well, it's actually okay to do so, okay? Because what we're doing here is we are talking about per Kelvin of change of temperature, okay? When we say per Kelvin over here, this Kelvin here is not exactly temperature, it's per Kelvin change of temperature. For every 1 Kelvin change of temperature, then of course this 175 minus 25 over here is also change of temperature. Okay, so if you are looking at the degree Celsius scale and you're looking at the Kelvin scale, let's say I start with 0 degrees Celsius. 0 degrees Celsius is equivalent to 273.15 Kelvin. I think you are aware of that. Okay, then 1 degree Celsius is equivalent to 1 plus 273.15 Kelvin, which is equivalent to 274.15 Kelvin. Okay, if I go on, then 2 degrees Celsius will be equals to 275.15 Kelvin. Okay, why do I highlight this thing? Because when I say that Kelvin over here represents change of temperature, then the delta T over here also represents change of temperature. I want you all to be very clear that every time we increase the temperature by 1 degree Celsius, it's equivalent to us increasing the temperature by 1 Kelvin. So 1 degree Celsius is equivalent to 1 Kelvin rise of temperature. If you drop your temperature by 1 degree Celsius, it's also a drop in 1 Kelvin of temperature. So 1 degree Celsius is equivalent to 1 Kelvin change of temperature. I'm not saying that 1 degree Celsius temperature is equal to 1 Kelvin temperature. They are not the same. But we know that every time we rise or drop our temperature by 1 degree Celsius, it's equivalent to us rising or dropping the temperature by 1 Kelvin. Therefore, we can mix up the two units in our calculation. But what we cannot mix up is, for the change in temperature, you cannot take your final temperature to be in Kelvin, your initial temperature to be in degrees Celsius, then that doesn't make sense, because you're taking temperature minus temperature. So the unit of the temperature need to be consistent. Okay, but for change of temperature and change of temperature, the two change of temperature unit can be interchangeable between degrees Celsius and Kelvin. Okay, so this thing, the unit should not mix up, but between alpha and delta T, you can mix up between per degree Celsius, per Kelvin for alpha, or Kelvin or degree Celsius for delta T. You can mix them up. Okay, so that's what that's area expansion for you all. Thank you very much.